Oh, good morning, folks. I just got out of a really rough and tumble Physics 204 lecture. I do not have, my wits about me this morning for some reason. So bear with me, um, as we go through the day today. Hopefully it will be a little bit smoother than my 204 lecture was, but I don't know. Maybe I just didn't get enough sleep last night, but I'm a little bit scatterbrained. I don't have any really major announcements for you, except that I'm still kind of trudging through your exams. I promise you I will have those as soon as I can. I know some of you have made appointments to meet with me about them. I can still absolutely meet with students who are concerned and who want to talk about strategies. But until I have a chance to finish those, it's going to be hard to analyze exactly what went wrong with your exam. But I am working as quickly as possible, given my very limited amount of time this week, to get through those so you can see not only how you did, but also start turning to your attention to next week, where we will have our next exam. I know, they're coming rapid fire, one right after another. The downside to that is that you have an exam basically every 2 weeks. The upside to that is you have plenty of exams, so if one goes poorly, then it's not the end of the world, and it'll kind of average out in the wash. With that said, I think it's maybe a little bit putting a little bit too much pressure on you to call them all exams, like midterms or something like that. Because in a course like this, you would normally only have like 1 or maybe 2 midterms, whereas here we have 5. So these are kind of more like super quizzes, I guess, is maybe a way to think about it. If there are anyone out there in the strange infinite void of the universe that would benefit from a little bit of de-escalation of the sort of intensity of these assignments, super quizzes is kind of like how I'd like to think about them. Definitely still an assessment, but not quite as heavy as a midterm exam that counts for 25% of your grade. Okay. With that said, like I mentioned, no real other major announcements. So today we are moving right back into where we left off, which was with conservation of momentum. Specifically, today we are going to be talking about collisions. Collisions, that is to say, when you have 2 or more objects colliding together, is one of the chief applications of conservation of momentum. So if you ever, you saw like a CSI show and some forensic scientist came in and like analyzed the scene of a crash, and they were like, oh, this car was going at this speed and they crashed into this one which was going at this speed, and that's why they ended up over here, that kind of thing. Those type of analyses can absolutely be done, and they involve conservation of momentum like we're going to be talking about here. Of course, we're going to be talking about much simpler versions than car crashes. Now, we need to get some vocabulary out of the way. To define a collision, it's just any interaction between 2 or more objects that results in a change of momentum of the individual objects. Now, the total momentum doesn't necessarily change, but the individual momentums almost certainly will. Now, collisions can be complex, but we'll limit ourselves to the simpler cases. So while you absolutely can talk about a car crashing into another car and all the damage that would come about from that, we're going to be more concerning ourselves with things like 2 billiard balls crashing into each other and going off in different directions. Now, to that end, there are 2 types of collisions that we're going to be learning about in this class. The first are elastic collisions. These are collisions where the total kinetic energy of the system is conserved in addition to momentum. So just to make a little note here, elastic collisions conserve momentum and kinetic energy. Inelastic collisions are those in which the total kinetic energy of a system does change. This is usually as a result of friction or something like that. And there is a special case of a so-called completely inelastic collision, where instead of 2 objects crashing into one another, they in fact stick together and become one single object. Sorry. 1 second. Okay, sorry about that. Where was I? Right. Inelastic collisions is when kinetic energy is not conserved, and there's a special case called a completely inelastic collision where the two objects stick together and functionally become one object. We'll try to examine each of those as time goes on. But the moral of the story here is that there are really just two equations that we're ever going to be applying in collision problems. Those are conservation of momentum. The final momentum is equal to the initial momentum, and conservation of kinetic energy, which will only apply to elastic collisions. So we'll use this for all, and we'll use this for some. And part of the process will be evaluating whether or not the collision is elastic. Now, you might ask, how will I know if a problem is describing an elastic collision? That's an excellent question. And the answer is very straightforward. The only time a collision is elastic is if you are told it's elastic. So the problem will either say two objects collide elastically, or for more sort of difficult, insidious problems you might run into in the textbook, it might not tell you it explicitly, but it will give you enough information to deduce that it is elastic. But by and large, for 90% of all problems, the way you know if a problem is elastic is because the problem explicitly tells you it's elastic. And that's the only situation you can use conservation of kinetic energy. Do not use this equation for any inelastic collision. This never applies to inelastic collisions, okay? Pause, make a note of that if you need to, because invariably somebody might make that mistake on an exam and they'll really regret it later because it's a very simple mistake to make. Conservation of momentum applies to all collision problems. Conservation of energy only to elastic collisions, and you will almost always be told explicitly when a problem is elastic. Okay, with that said, that's all. That's all the vocab. Everything else is we're just going to look at collision problems first in one dimension and then in two dimensions. Okie dokie. Here we have a 2 kilogram block slides along a frictionless surface at 1 meter per second. A second block sliding faster at 4 meters per second collides with the first from behind and sticks to it. What is the final, what's that word? Final velocity of the combined block. The final velocity of the combined blocks is 2 meters per second. What is the mass of the second block? Step 1, always step 1. Elastic or inelastic? Answer that question. That's the first step always. We look at the problem, we read the problem statement. There is no mention of it being an elastic collision. So this is not an elastic collision. So we will not be using conservation of energy. Furthermore, we actually have additional context clues that really hammer in the fact that this is inelastic. Namely, that the blocks stick to one another. By sticking to one another, this is actually the special case of a completely inelastic collision where the two objects stick together and functionally become one object. We'll see what we mean by that here in a moment. So this problem has two pieces of information that tell us that this is an inelastic collision. The first piece is that we are not told it's elastic, therefore it's not elastic. And the second is that the two blocks stick together. A second step for problems like these is usually to kind of draw a picture, just helpful, like a kind of before and after picture. This is just to kind of help us visualize what's happening here. So we have a block. We have a block that's sliding along at 1 meter per second. And we have another block that's going at 4 meters per second, sliding up behind it. Now, what we're told is that these two blocks stick together and then move together at 2 meters per second. Additionally, we're told that the initial block has a mass of 2 kilograms, and we don't know what the unknown mass of the other block is. And that's what we're solving for. So this is going to be a direct application of this formula here. And we just write it down. The mass of the first block times the initial velocity of the first block, the mass of the second block times the initial velocity of the second block equals the mass of the first block, final velocity of the first block. Those should have subscripts. And the mass of the second block, final velocity of the second block. We always just start by writing down conservation of momentum. And we do that because this is almost always going to be used in any collision problem. And at that point, frankly, you can probably just start plugging things in. We are told the first block has a mass of 2 kilograms and is moving at 1 meter per second to begin with. We don't know the mass of the second block, but we know that it's moving at 4 meters per second. And we know that both of these blocks, both the 2 and the unknown, they are both moving at 2 meters per second. So this gives us 2 plus 4m equals 4 plus 2m. Now I just have to isolate my mass and solve, so I'll subtract 2 over onto both sides. So this is going to be 4 minus 2. I'm just going to subtract 2m over on the other side. So this gives me 4 minus 2 times mass equals 2. Well, that's also 2, which implies that my mass is 1, unless I haven't made any algebra mistakes, which is entirely possible. So you can see this is just a one-step solution using conservation of momentum. Here's a hint, folks. If you're doing a collision problem and you're not using conservation of momentum in some way, you're almost assuredly doing that collision problem wrong. All collision problems will involve conservation of momentum in some way, shape, or form. So this was an example of an inelastic collision. And it is worth noting that because these two velocities up top are the same, they're both just v, I could theoretically have factored that out like that on the right-hand side if I wanted to, and that might be a trick that becomes useful to you when you're doing problems down the road. But this is just an example of an inelastic collision. There are, in fact, others. Here's another problem. Here we got billiard balls. Now, we're being told that they are nearly elastic. This is just a statement about billiard balls in general. In real life, billiard ball collisions are, in fact, nearly elastic collisions. Now, in one such collision, the cue ball approaches the 8 ball at a speed of 2.7 meters per second and strikes the stationary 8 ball in a one-dimensional collision. Ignoring the spin of the balls and assuming that the collision is elastic, what are the velocities of the balls after the collision? Right there, that is our key phrase. Assuming the collision is elastic. That is telling us this is an elastic collision, so we can use conservation of kinetic energy in addition to our conservation of momentum. Now, we are going to approach this problem in a very general way. where, or rather a very specific way, which is we're going to assume that the billiard balls have the same mass. This is not always the case, however, so actually it might be better if we start off by just labeling these M1 and M2. Who knows? Maybe they do have slightly different masses. We're not actually told anything about that in this problem. Now, what we're going to do now is we're just going to apply conservation of momentum. And we'll note that when we write down conservation of momentum, M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. Note that the only thing we can do in this equation is we can simplify by noting that my second billiard ball, my 8 ball, has an initial velocity of 0. So that term is going to go away. And my conservation of momentum just becomes that. Now note, this problem is asking for the velocities of the balls after the collision. So we want to know both of these velocities. So that means we have two unknowns, but we only have one equation. We cannot solve this yet. That's where conservation of energy comes into play. Now, for the same reason as before, since the 8 ball starts at rest, this other term is going to go away. And you'll note that there's a factor of 1/2 in every term, so those can be canceled out. So my second equation would be M1 V1I squared equals M2 M1 V1F squared plus M2 V2F squared. I have two equations here. Theoretically, I have two unknowns if we're given the mass of these balls, but this is the most general solution for a problem like this one. And if you're looking at that and saying it would be a nightmare to solve, you are correct. It is a Herculean algebraic effort to solve these two equations simultaneously, so we've done it for you. These two orange equations are the solution for when the two objects are in. There's a question in the chat, why does the 1/2 cancel out? Because it's in every single term of the equation. You can divide both sides by 1/2 and they'll cancel out. In the same way that 2x equals 2y, you can divide both sides by 2 and get x equals y. You can do the same thing here. You just multiply every term by 2, and they cancel out. That's just algebra. So hopefully that's a little bit more clear now. These two orange equations, which I've put in giant letters, will in fact move off screen so you can see them clearly. This is the general result for an elastic collision when V2I equals 0. That is to say, one of the objects starts at rest. There's another question in the chat. Could you not do the same with M1 and M2? If M1 and M2 are different, no, you absolutely cannot do that. And that was the primary assumption I was making here. Yes, we're going to see that when we actually try to finish solving this problem, they will cancel out. But right now, those are different numbers. So no, absolutely not. They cannot cancel out the way I've written them here. I could cancel out, say, M1 from one of the terms, but then it would still appear in the other. There's no way to cancel out the masses based on what I've written here. Come on, PowerPoint. There we go. So these results you might find useful on your homework. You can just jump right to here on the off chance that the two are 0. There's another question in the chat. If the 1/2 always cancels out, what is the purpose of having them at all? Because mv squared is not kinetic energy. So we are writing down a base principle, conservation of kinetic energy. Kinetic energy is 1/2 mv squared. If I just tell you to always write down, cancel out the 1/2, then you're going to be having to remember two different equations, conservation of kinetic energy and whatever the result of that is. And we'll also find that this only cancels out in the specific case when kinetic energy is the only energy that's being conserved. If we had potential energy being conserved, for example, that we would not be able to cancel out the factor of 1/2. So, as I was saying, very good questions, but I should really just wait till I finish my thought to go back to these. I apologize, folks. I'm getting flustered, but it's not your fault. It's my fault because I'm answering the questions mid-thought. I just need to wait until I'm done. That's on me, not on you. As I was saying, these two equations are the very general result that apply to all cases for elastic collisions when one of your objects starts at rest. So you can just use these orange equations when you're doing your homework, for example. All right, so in this specific problem, it is actually safe to assume that m1 and m2 are the same, and so we'll just call those the variable m. So now we see here clearly m minus m over m plus m, v1i, v2 f equals 2m over m plus m v1i. If I assume these have the same mass, I actually just get 0 and v1i. And if you've ever watched say, professional pool, you've probably seen scenarios in which the cue ball hits another ball and it just stops and the other ball goes. That is a perfectly elastic collision, and it's what's being represented here. But the more useful result is the very general solution for elastic collisions that can be applied more or less everywhere. All right, this was a somewhat abstract exercise, and based on the number of questions I got, I do not think it went over well. So maybe we should just try to do a actual problem that will get a numeric result. All right, so we write down conservation of momentum, and we write down conservation of energy, and I forgot my subscripts on all of these. That's my bad. Here we have an air track and carts that are often that we often use in our physics laboratories. Not that you folks, unfortunately, are able to use them because of COVID, but we often use air carts to crash them into each other and sort of do collisions between things. And so, this is a common way of experimenting and analyzing collisions. In this particular case, we have a nearly frictionless track when air is forced through the holes. And in the figure below, we have a cart that moves in the positive direction with a speed of 19.8 centimeters, while cart 2 is at rest. The collision is elastic, and M2 is equal to 2.4 M1. This is a good example of an elastic collision where the very simple case will not work out for us. But we can, in fact, combine these for elastic collisions. And you can do the algebra. In fact, I encourage you to do the algebra once, just to really convince yourself that it's true. But when we do that algebra, we get that V1F is equal to M1 minus M2 over M1 plus M2 times the initial velocity of 1. And then V2F is going to be 2 times M1 over M1 plus M2. Now, it would be very, very cruel of us to ask you to do this algebra on an exam, like to actually ask you to do it out. So it is my hope and my expectation that if we're going to give you any problems like this, we'll probably give you these versions. Not because I want you to, have to remember more equations. In fact, I already chastised myself about, writing down the factors of 1/2 here, because with this factor of 1/2, then this actually represents conservation of kinetic energy as opposed to representing something that looks kind of like kinetic energy. But in this particular case, these two additional equations, if I can convince Dr. Tamaro to put them on the formula sheet, are super useful because the algebra here really is not in any way, shape, or form trivial. Certainly not for our exam. So with any luck, we'll be able to use these. Now, with that said, once we have those, it's a matter of just kind of plugging and chugging. In this particular case, let's solve for the final velocity of cart 1 first. So you'll note that I am not told what M1 is. But I am told that M2 is 2.4 times M1. And so I plug that in to my expression. What that allows me to do is factor out from both the numerator and the denominator that factor of mass. So I get 1 minus 2.4 over 1 plus 2.4, which means that these masses will cancel out. Now, at that point, it's just a matter of plugging in my values. I've got 1 minus 2.4 divided by 1 plus 2.4. You'll note a couple of things. One, this gives me a negative number, 0.412, multiplied by the initial velocity of 19.8 centimeters per second, which gives me negative 8.15 centimeters per second. This negative sign is important because it implies that after this collision, M1 starts moving backwards in the opposite direction, whereas we assume M2 is going to move forwards. Sure enough, we can confirm that. I'll get out of the way by just plugging in our 2m1 over m1 plus 2.4 m1. Once again, we'll see that I can pull a factor of m1 out of both the top and the bottom. And when I calculate that result, so that's 2 divided by 1 plus 2.4, multiply that result times 19.8, I get positive 11.6 centimeters per second. Where are we? This one, M2, will head off to the right with a larger velocity, than M1 will move backwards. Okay, that's an example of an elastic collision that you might actually be asked to, actually evaluate. And again, I emphasize you should go through the algebra once to see if you can. It is worthwhile doing because it will help you understand a little bit better where these equations come from, and it may help you on your homework. Okay, now at this point, I am actually going to do my due diligence, and I'm going to pause. And rather than allow myself to get distracted, because I'm already scatterbrained enough today, I would like to ask the chat if you have any additional questions. And because I forgot to set this to low latency, it means I'm going to have to wait a moment for that question to propagate. So I'm just going to sit here and enjoy a sip of my coffee and have a sort of calming, centering moment while I ask if there are any additional questions in the chat. Ooh. Goodness, folks, I don't know what to tell you. Sorry if I'm a little off today. It has been a week already, and it's only Wednesday. I'm sure you can all relate. The first question in the chat is that vector sum equal to the vector of object 1? Michael, I'm not sure I understand which vector sum you're talking about. Are you talking about the addition of the two final velocity vectors, if those will somehow add up to the initial? And the answer is not quite, kind of, but not quite. They'll add up in a sort of like weighted sum, like a weighted average, so to speak, that are kind of modulated by their difference in masses. And ultimately, the way that happens is through the equations we have written here. So what I'd say is that they're related, but it's not just a simple vector sum, no. And if you were asking something else, you can clarify that in the chat. There's another question. How did I get 1 minus 2.4 over 1 plus 2.4? Yeah, you know what? That bears a little bit of explanation. So yeah, let's ignore this scary thing. That's for Physics 204. I'm just going to pull up my whiteboard. So this is a question about I was evaluating the equation 1f equals m1 minus m2 over m1 plus m2 v1I. And let me just make sure I, in fact, copied that down correctly. Yeah. And I'm using the fact that m2 equals m equals 2.4 m1, which is given to us in the problem. So just to be clear, I'm using this relationship right here and this equation right here, just so we're on the same page. Now, once we get to that point, the very first thing that I do is I take this relationship and I plug it in for each of those m2s. And I'm going to color code this just to make it a little bit easier to see what's going on. So it's 2.4 m1 in both of these cases. Now, the next step is actually to look at both the numerator and the denominator separately. Now, if I were to look, for example, at the numerator, m1 minus 2.4 m1, I can factor out m from both of these terms. Now, this term, it's pretty obvious. There's just that coefficient of 2.4. But remember, whenever there isn't a coefficient written down, you can assume there's like an imaginary coefficient of 1. And maybe what I'll do is, just to keep the number of sig figs the same, I'll write that as 1.0. So when I factor m1 out of this first term, I am left with a factor of 1. I can do the same thing on the bottom. Whereas I get a plus instead of a minus. Now when I take those results and I plug them back into my formula here, I'll have an m1. I'm going to have to use some complicated parentheses here. 1 minus 2.4. And an m1, 1 plus 2.4. And it is at this point that these m1s clearly cancel out. It's just a fraction. m1 over m1 is 1. And that's what gives me my final result of 1 minus 2.4 over 1 plus 2.4. Hopefully that cleared that up. Okay. Any other last minute questions before we move on and talk about the sort of one sort of complicating factor that comes into doing these collision problems? I really got to remember to set my stream to lower latency. Something I will consider for future lectures. Okay, I'm not seeing any other questions in the chat, so I'll mumble a bit, and if I see more, I'll address them at the end of my rambling. And, of course, PowerPoint doesn't want to go forward. Now, the one sort of complicating factor here is that in addition to one-dimensional collisions, just two things traveling on a line and crashing into one another, I can also have two-dimensional collisions. That is to say, maybe I have two cars coming to an intersection in opposite directions. They crash into each other and go off in another direction. Now, this is going to seem a lot more complicated, but it's actually a little bit straightforward. Because if you think back to how we treated kinematics in two dimensions, we just took the same equations and we applied them completely separately. Here, we're going to do the same thing. We're going to apply conservation of momentum separately, independently, to both directions. And gosh, I forgot all of my subscripts in here. This is so bad. I'm going to actually have to re-upload the slides after I fix that, because this is just unconscionable. So what this means is you apply conservation of momentum to each direction using just the components of the velocity in that direction. Now, this will take a little bit of getting used to, but it is doable based on what we've done back in Chapter 3. So if you were a little bit uncomfortable with projectile motion and you kind of identified that as a weak point sort of like after the first exam, like this is now a time for you to really make sure you are comfortable handling two different directions. But it does beg the question, what about kinetic energy? Do I also get two formulae for kinetic energy? The answer is no, I do not. Oops. Because kinetic energy is a scalar value, meaning it's just a number, no direction. So we still use the same 1/2 m1 v1 squared plus 1/2, it's I, 1/2 m2 v2 I squared equals, the same thing that would be written down in all of these other cases is used unchanged here because kinetic energy does not have direction. And I'm standing in front of it. So nothing changes about kinetic energy. Let us see an example of this, assuming I can label all of my subscripts correctly. Here I have a car that has 1250 kilograms that's heading west at a certain speed. So this one is the 1250. And this one is the 1450 police car traveling north at a different speed. And the two crash into each other. They stick together. They have the same final velocity, completely inelastic collision. We want to find the magnitude and direction of the final velocity of the cars. Okay, so this is a scenario where I suspect if we just look at this, we immediately get concerned because, this is two dimensions. That invariably makes it seem and feel a lot more complicated. But we're actually going to see that the fact that this is in two dimensions helps us quite a lot. Now, the reason for that is a couple of things. First, these two cars stick together, which means two things. One, it's a completely inelastic collision, so we don't have to worry about conservation of energy, because that only applies to elastic collisions. Two, they stick together, so they have the same final speed, which means the x components are equal to one another and the y components are equal to one another. So if I rewrite these equations, that means m1 v1 in the initial velocity for car 1 in the x direction plus m2 times the initial velocity for car 2 in the x direction will add up to m1 v the final x plus m2 the final x. Note that because those two final velocities are the same, and again, this is because they're sticking together, I can factor that out like so. Additionally, if I look at these two cars, note that my car is only traveling in the x direction, so car 1 has no initial y component. And similarly, my police car is only traveling in the y direction, so it has no initial x component. That means this term here is 0, which leads to a very simple equation that I actually have enough information to solve directly. I divide both sides by m1 plus m2. I know the masses of both cars, so it's going to be the mass of car 1 divided by the total, and I'm going to multiply that by the speed of car 1. So this would be 1250 over 1250 plus 1450 times negative 15.6 meters per second. Note that it's negative because this car is moving to the left. Remember, to the right is generally assumed to be positive. And that's just a number. I mean, I can just calculate what that is. 1250 divided by 1250 plus 1450. And then I'm going to multiply that result by negative 15.6, and I get negative 7.22 meters per second. I'm going to end up with a very similar situation down here. For the other direction, I'm going to run out of room here. That's fine. I'm going to get m2 v2iy equals, I can factor out the final y velocity, and I'm going to end up with an equation very similar to my first one. So I'm just going to have to do m2, 1450, divided by the sum of the masses, and I multiply that by the y velocity of this car, positive 11.2. Assuming I haven't made any calculator errors, that gives me that Vy is going to be positive 6.01. And just looking at the diagram, this seems to be visually consistent. My x component is only slightly larger than my y component, and it is to the left and up, corresponding to the negative and positive. So we're done finding the components of the velocity, but this problem is asking us to find the magnitude and direction. Remember, those always come about via Pythagorean theorem. So the sum of the squares of the two components. And in this case, that's just going to be negative 7.22 squared plus 6.01 squared. Then I take the square root of that answer, and I get that the final velocity is 9.39. And similarly, I'm going to get out of the way. I have to do the arctangent of the components. You remember that the way we do this we have to be a little bit careful about what triangle we're looking at. The way I would probably recommend us to do it here is just to find this angle that's indicated in the problem, theta. As a result, we're doing the arctangent, but I'm just going to take the magnitudes here just to make sure that I'm getting the actual angle. And when I do that, I get 39 degrees. Can I go over why the second part of the equation is 0 again? You're going to have to be more specific. There are a couple of equations where there are zeros here. I think you're talking about this one, and that's straightforward. Insofar as this car has an initial velocity in the x direction of negative 15.6, and it has an initial y velocity of 0. Similarly, the police car has an initial x velocity of 0, an initial y velocity of positive 11.2. So the x component for my second car is 0, and the y component for my first car is 0, which is why each of these terms go away. Let me know if that did not clarify your question. All right, we are just at the top of the hour, which is, or coming up to the end of class, because now we are actually done with collisions for now. Next class on Friday, we'll talk about the center of mass, and then we'll be done with Chapter 7, and that will be all of the content for Exam 3. Chapter 6 and 7, conservation of energy and conservation of momentum, are going to be what's on next week's exam, and I will provide you a study guide as soon as I have one. After that, I think we're going to get a little bit of a breather. Our exam schedule shifts so that we'll be taking future exams on Fridays. This is as a result of two things. One, Election Day is Tuesday, the first Tuesday in November, and Veterans Day is the following Wednesday, so that kind of messes up our schedule a little bit. So Exam 3 will be next Wednesday. Subsequent exams will be on Fridays. If you have any questions, comments, or concerns, book an appointment with me on Starfish or come to my walk-in office hours. They're going to be starting here in about 10 minutes. You can also shoot me an email. I have limited availability after my office hours are closed, but I'm actually kind of booked up with meetings most of the week. If you need an exception and you really, really, really desperately need an evening time slot, you can shoot me an email and we can try to work something out. Otherwise, something to consider is that Dr. Tamaro, I think, has weekend office hours that you might find beneficial, and we can talk to him about having you poke your head into those. With that said, we are done for the day. Thank you for bearing with me. I was a little out of it, and hopefully that wasn't too detrimental. But we will touch base again on Friday and wrap up Chapter 7, folks. Otherwise, have a good week, and I'll see you then.